Hello everyone, Dr. Shane here. This may be one of the shorter videos. So we're looking at, whoa, there we go. This is just the draft. We're still revising these. I'm making these in advance. In fact, I'm making this video right after lab, after you did your last spectroscopy quantitative analysis lab. Okay, so this is the graphical determination of order. This is I think our last kinetics experiment. This is a really good one. This drives home a lot of points. So we're looking at integrated rate laws. So those are the integrated rate laws for zero, first, and second order you learned about in lecture. So this is where we are. And I don't think I have too much to say about the procedure because it's pretty straightforward. So let's go and see how far we get. Okay. All right, so the first thing is you've actually done these calculations for this lab, but maybe you didn't understand all of them. So back in weeks 1 through 3, you did a bunch of review problems from Chem 125 or whatever first semester lab and lecture 121, whatever you had, and then you did a bunch of Excel activities. So I'm not going to re-upload all of that stuff. I don't think I need to do that. So it's still on D2L under weeks 1 through 3. So what you want to do is go back and look at that last Excel activity from weeks 1 through 3. That's what it is. And just kind of remind yourself what you did. It was a long time ago. Also, in that handout, if you will, or that document, there's a link to a YouTube tutorial about Excel. And around minute number 19, that's when it starts on these set of calculations right here that are like this. So kind of look at that, remind yourself how you did it, or at least have it there as a reference. So minute 19, that'll save you some time listening to that whole thing. And that's about when it starts. It's a little bit after minute 19. So if you need to, stop the video and get organized, find the YouTube tutorial, find the Excel spreadsheets that come along with this. Basically, I give you one spreadsheet where it does all the work for you, and then we asked you to reproduce that data and get those answers. And if I remember right, it was difficult to tell if it was first order or second order. They were both pretty linear. I'm going to get to that later. Okay. So if you really know what you're doing, and all I'm going to ask you to do is to repeat what you did with that set of data from weeks 1 through 3 in Excel with a new set of data. And I'm actually giving you the answers. It is a first order reaction, and the rate constant is 0.125, and if it's first order, you should be able to figure out what the units on the rate constant should be. So I'm going to leave that kind of as an open-ended one here. Okay, so also, I'm not sure you can read all of these data. What I have on the board here, rather than typing it into a spreadsheet and giving it to you, you can just go to a spreadsheet and type this data in yourself. In fact, what you might want to do is take the spreadsheets that you used weeks 1 through 3 and maybe copy and paste them. That's probably the best way to do it, actually. Copy or make a new worksheet and then enter the data in the same slots that you did those first. I think it'll make more sense when you do that. I'm just trying to keep this video simple because I think you'll figure it out. So look at it, and on the spreadsheet I give you some data. I think in the spreadsheet original spreadsheet I gave you a temperature of 20 degrees Celsius. So in this case, we're going to do something a little different. We're going to assume that we do this chemical reaction at something a little bit higher temperature, so 50 degrees. The atmospheric pressure is a little different, so it's than what was given before. The stock solution of the HCl is still 6. Whoops, I didn't put molar there. And the total volume of the reaction mixture that you're doing is still 45. I'm going to talk a little bit about the procedure with the handout, but you can see I don't even have any apparatus here. This is just a bunch of stuff that I have up here from left that I was just looking at before. So I'm not even going to describe the apparatus. It's pretty straightforward, but I'll come back down and use the pictures. Okay, so what we're asking you to do for your pre-lab is to calculate, determine the order of reaction. So what does that mean? So you want to rule out zero order and second order. It's first order, okay? And the grade constant is 0.125. So we're still doing 10 minutes of data collection. The volume of hydrogen is given right here. I calculated these volumes, so this is perfect textbook data. So it should be clear that it's first order. Very clear. Maybe not hugely clear, but it's definitely going to be first order more than the other two. So I'm not going to describe this too much, but if you want to write down the data, maybe I'll just read the data off. So the times are 0 to 10 minutes, just like we set up in the lab, just like in the lab manual. And you're measuring volume every 10 minutes, and if you need me to read them off, at 0 minutes it's 0 volume, 9.4 milliliters, 17.6, 24.9, 31.4, 37.0, 42.1, 46.5, 50.4, 53.8, and 56.9. So you can get all of this onto your Excel spreadsheet. Now, I'm going to erase some stuff here. I think we're good to go. I don't think we need. Just make sure you have all this data down. So, on the spreadsheets from week 1 through 3, you have a model for how to do all these calculations. So to calculate, like, I'm just going to give you a brief. To calculate the moles of hydrogen, we use PV equals nRT, and N, we're trying to solve for moles, so it's going to be PV over RT. So the temperature has to be in Kelvin, so that's 50 degrees Celsius. Okay, so make sure that's there. R is 0.08206. Make sure you use that one, not the R we've been using in lecture this semester. Pressure is the atmospheric pressure that I gave you converted to atmospheres. And the volume is, well, this volume converted to liters. Now, that's fine. You can do that, and actually what you should probably also do for your pre-lab is show a set of calculations for every one of these by hand so that you show that you know what you're doing. So, so you're not just copy and pasting formulas from the Excel spreadsheet I gave you onto here, which if you're really confused, you can do. But you really should do a set of data showing it step by step, and then let Excel do all the rest of the work. That's what you're going to do in your calculation section here anyway. Okay. So you'll show one sample calculation, and then Excel can do the rest. That's very standard. So why don't we just put that as a pre-lab question. So pick for time equals 1 minute. So you're not using the time. But for 9.4 milliliters, do all these calculations. Fine, so that's the first column. To get the number of moles of, let's see, so that's that one. So the number of moles of HCl lost, that's where we go to the chemical equation. I can't remember if it's magnesium or zinc that we're using. It doesn't really matter, it's magnesium. It's a 2-to-1 ratio between hydrogen, moles of hydrogen, and HCl. So I think you're multiplying by 2 to get the next column. Okay, again, I don't want to just kind of hand you the calculations. Part of your job is to explain how do you do this calculation, this calculation, this calculation, and this calculation. And you'll do that in your calculation section. And you all, again, you have a model from before. I probably keep saying that too many times. So that just kind of gets you started. Always go to your instructor for office hours if you need to. So you generate all these data. What you want then, this is a review. If you know what you're doing, you don't even need to watch the rest of this video. You're like, I got it, I know what I'm doing. You already showed us in the video, starting at minute 19. Remember what you're doing for integrated rate loss to determine this. So you've got the 3 equations right there. So for 0 order, you graph, well, your graph, these are just using generic symbols A. So what are you using? Well, you're going to put the concentration of HCl, this column, versus time. And see if that's linear. That's for zero. That's for zeroth order. For first order, you're going to do the natural log of the concentration of HCl versus time. And that's the one I told you, that's going to be dead on. It's going to be pretty much every data point is going to be on that line. It's going to be the highest correlation coefficient, and you should get the slope of this line is going to be negative about this. And again, I'm not going through every detail here, but the slope of the line is the negative rate constant. The rate constant is always positive. Again, that's a detail from lecture. And then for second order, you graph reciprocal concentration versus time. And again, these two won't be as linear as this one. I'm telling you the answer just so you know exactly what you're doing when you come in the lab. So I think that's it for the pre-lab, other than to do all your other pre-lab activities. So do the analysis that we did during weeks 1 through 3. Go back, look at the example I gave you on those spreadsheets of one workout. Go back to the YouTube tutorial if you need to. And also, you don't have to do this, but the rate constant is higher because the temperature is higher. Okay? Also, we're collecting a lot more volume because the temperature is higher. The rate of the reaction is going to be faster. That doesn't change the order. It's still first order. Okay, that's probably enough. In terms of procedure, well, you've got a picture of it right here, right? This is going to be set up for you. At your individual lab station, this apparatus is going to be right there. Or Dr. Kegaris, and I think I might help him, is these will be set up individually because we'll never finish it otherwise. It's pretty straightforward. You read through the whole lab, and I'm just going to jump to the procedure. So you're going to take some 1 molar hydrochloric acid that'll be on your bench, that's fine. And this is a very rough solution. So let's see, what are you doing? You're putting 6 milliliters of HCl into a 50 mil graduated cylinder. So this is not a very precise solution because we're not using any volumetric glassware. Well, this is not great volumetric glassware. And then you're making a total volume of 45 mils, so adding water to it. And then you pour that into a beaker. So that's not a super precise solution. But to get the molarity of that's pretty easy. It's just a M1V1, M2V2. That's pretty easy. And that's part of the calculations that you'll need is the molarity of this solution. Yeah, okay. I don't think I even want to go through this all that much. So the main thing we're going to do well, I'm going to come down here actually, look at the picture. I guess I could make a better video. So this is pretty straightforward. So what you're going to do is, yeah, okay. So you're going to have a bunch of magnesium down here. You have way more than you need. So magnesium is way in excess. And I think what you end up doing, this is super easy, is you pour the HCl solution from the beaker in here and it starts making hydrogen right away. So you cap it and then pressure builds up over here. In this is just water. This EM is Erlenmeyer flask. And so the hydrogen gas comes over here, builds up the pressure, and then forces water out through this tube. And we assume every milliliter of water we collect here equals 1 milliliter of hydrogen gas. So when you hit the stopwatch, and every minute you just record the volume of water on this. It's pretty straightforward. The main thing is to make sure everything's sealed up, but I think we're going to handle that in those details in lab. So it's pretty easy. Like I said, your reaction happens here, hydrogen gas comes over, the gas pressure builds up, pushes water out, and then you collect water here which is what we record as volume H2 in milliliters. We assume that those are the same. I think that's about it for the procedure. Yeah, so we test the procedure, but I don't think it's really worth describing all of that testing of the procedure, because once the apparatus is working, it's pretty straightforward to do. You have a stopwatch, okay. Yeah, there may be a lag time in the collection of water. It takes a little while for the vapor pressure. Well, actually, that should just be gas pressure. This is a rough draft. The gas pressure of hydrogen builds, and it may take a while before you start to see water collect. And let's see, when do you start the stopwatch? Yeah, once you start to see steady drops, you can hit the volume, or excuse me, hit the stopwatch, and you collect, yeah, okay, that's fine. I think that's pretty straightforward. And we use 10 minutes here, but if you're not too sure, or you think you did something wrong, you can collect more. And, oh yeah, there's some other data we're gonna need from the room, right? We're gonna need the barometric pressure, which we'll get from the back room. I may forget all of this, you have to tell me. We'll need the temperature of the room, which I'll make sure, I can write this on the board, but you may have to tell me all that. And I think that's it. Yeah, the temperature of the room and the pressure of the atmosphere. And if you haven't never seen our mercury barometer, it's really cool. It's back in our stock room. It actually has mercury in it. So if you haven't seen it yet, let me know and I will show that to you. And cleanup is, we just leave the apparatus out. Okay, talking through the lab right now. So the first calculation is to calculate the molarity of the HCl into the beaker that you made. That's just the dilution calculation, right? Okay. Then number 2 is really a lot of work. So number 2 is where you calculate for each of your data points, use the ideal gas law to get the moles of HCl, use equation 4, which I think is the chemical equation. Yeah. Then you calculate the HCl, oops, yeah, that's the HCl loss. Then you calculate the HCl present. Go to the video for this one. And then you get the moles of HCl that are in the reaction mixture, and then you convert each of those to a molarity by dividing by the total volume. Again, all this I think is laid out pretty much detailed there, so it should come together nicely. What then are we doing? Number 3, use the information from calculation 2, which is actually 3 calculations. So number 2 has 3 parts. That's where the majority of the work comes in. Oh, I'm sorry. So number 3 is actually the molarity. Okay. Yeah, so calculation number 3 is this last column. That's calculation number 3. Then number 4, using the information from calculation number 3, graph the appropriate relationships, test for linearity for the correct order, make 3 graphs, figure out which one's the most linear, get the rate constant, which is another pseudo rate constant, which is fine. It's a rate constant. And then, determine the half-life, that's fine. Once you have the rate constant and you know the order, you can calculate the half-life. I forgot that was part of it. So once you know the order, you know the half-life equation. To calculate the half-life, you need to know the K. Okay. I didn't put this in here as a pre-lab question, so if you're watching the whole video, you can calculate the half-life for this. You don't have to do that if you don't want to. And I think that's it. I said that was going to be a short video, didn't I? Not that short. So there's not much to say about the procedure, but see how far you can get with this. Again, you have a model set of data. If nothing else, and you end up cutting and pasting, okay, just keep in mind that when you write your lab report for this lab, you'll have to show some calculations showing the work, like writing it out and showing sig figs and all that stuff, to prove that you know what the Excel's doing. You're not just taking Excel, what I gave you, and just using it as a black box, if you will. You just throw the data in and it gives you answers out with no understanding. Okay, that should be it. So we'll keep the video pretty short, and that should be good. All right, we'll see you in lab.